Yes, I am audible.
Yes, sir, audible.
Yes. Yes, video is off. Yes, no, because I'm out of station. Yes, no. Okay.
Okay, sir, no problem.
Yes, today topic is electronic spectra and Raman spectroscopy. Yes.
Sir, Raman spectra first and then electronic spectra.
Yes, first Raman. Okay, no problem.
Yes.
Yes. So first of all, let me start basic introduce yourself.
Yes, sir. I am Momita Sarkar. I am from West Bengal. I was born in Coach Bihar, West Bengal, from where I have done my schooling and high schooling with 91% and 89% marks respectively. Then I have done my graduation from Acharya Brojendranath Shil College, A grade, Coach Bihar, with 82.3% in honors, and then I have give IIT-JAM examination, and through this I have done my masters from Indian Institute of Technology, Patna, with 78% marks, and I have also qualified GATE and also PARK written exam.
Yes, good. Yeah, let me start. First of all, basic is Raman spectroscopy. What is Raman spectroscopy? What the main application of Raman?
Sir, Raman spectroscopy is basically the light scattering phenomena. Light scattering phenomena means when a particle or when a 1 minute, sir. Raman spectroscopy is basically light scattering phenomena. It is not any absorption phenomena like all other spectroscopy. So when an electromagnetic radiation falls on a sample, and the electromagnetic radiation has scattered electromagnetic radiation at intensity I0, and then it radiates some scattering some scattering radiation which has wavelength same or other. If the wavelength is same, then it is Rayleigh scattering, and if others, then if wavelength is different from the incident frequency, then it will be Raman scattering. And basically through Raman spectroscopy, we see the molecule is polarizable or not, and we also see that the molecule is to determine the polarizability of the molecule, we did Raman spectra.
Yes, good. Yes, first basic is Raman spectroscopy is Stokes and anti-Stokes and relay lines. What the main objective of Stokes, anti-Stokes and relay lines in Raman spectrum? Describe.
Yes, sir. Uh, Stokes. Sir, it is relay scattering. In this case, basically we have take two state, that is initial state, final state, and we contrast to the another contrasting to the another spectroscopy. In this case we have an virtual state. So when the molecule excited to the initial state to virtual state at first, and then the molecule come in the final state, if they give the same wavelength with the incident wavelength. So that means the molecule not taking any energy from the photon molecule, and also the molecule is not losing any energy to the photon molecule. Photon means when we give a light frequency and the light is consisting of photon. So when we give a light with frequency nu, and that is consisting of photon molecule in a sample, then basically after some time it give a scattered frequency with same nu and same wavelength, then it is Rayleigh scattering. But in the second case, if the molecule is excited with a radiation of frequency nu, that is consist of photon molecule with h nu 1, and it go from initial state to virtual state, but after some time when it returns to final state, final state uh, final state, then the wavelength or nu is not same. In this case, wavelength become larger than the initial wavelength, but frequency nu getting smaller. So in this case, that means the molecule gains energy, and when molecule gains energy, in this case lambda getting become larger and frequency getting become smaller. So it is Stokes radiation. And in the case of anti-Stokes radiation, the molecule excited from final state to virtual state, and then it come back to the initial state. So when it come back to the initial state, in this case the frequency become changing, frequency getting higher to the comparing to the initial state, and lambda getting smaller compared to the initial lambda. So it is anti-Stokes line. In the case of anti-Stokes line, we see the intensity of the spectra getting decreased, because in this case the molecule excited from final state. So in the final state, the molecule our population is less. That's why anti-Stokes line has less intensity than Stokes line.
Yes, good. How many factor affecting in Stokes, anti-Stokes, and Rayleigh lines?
Sir, 3 factor. One is the wavelength, and another is the frequency, and another is the temperature. Three factor.
Yes, wavelength, energy,
Like, and temperature.
yes. What the value of energy, frequency, of temperature in Stokes and anti-Stokes line?
Sir, value is exactly not remembering, but the basically in the range of nanometer range, like 10 to the power 7, 10 to the power 7 divided by something 3827 in nanometer range.
Yes. Yes, what the collision in Raman spectroscopy from elastic and inelastic?
Yes, sir. Collision. So, sir, when a light of intensity is, if we explain this, yes, if a light of intensity is with frequency nu interact with a sample. The sample may be solid or liquid or gas. So if the sample is basically the nucleus, and nucleus is embedded in a electron, so when the light falls on that sample, then due to coulombic interaction, the positive poles and the negative poles moves away from each other. So in that time, the light frequency interact with that, and therefore in that case dipole moment generate. And when dipole moment generate, so light frequency interact with that dipole, that means charge. From this case, the molecules orbit perturbed, and when they getting perturbed, and therefore their size changing, and their polarizability getting changing. Polarizability means the distance of the degree of distance of electron from their nucleus. So it is basically the collision occurs with light frequency frequencing proton with the samples.
Yes, good. What is Raman shift?
Raman shift is lambda h nu minus h nu dashed is equal to h into 1 by lambda Sir, Raman shift is basically we get from this formula, that is, it is the difference from the incident wavelength with the scattered wavelength. Like if the frequency in which exciting frequency, and from exciting frequency we get a wavelength, and then the scattered frequency, and from that also we get a wavelength, and the basic difference between these two is Raman shift.
Any red shift, blue shift in Raman?
Red shift, blue shift in Raman. Sir, no, the red shift and blue shift occurs in electronic spectroscopy, I know.
Yes, right. Next is, what is rotational Raman spectra? What is rotational Raman spectra?
Yes, sir. Sir, rotational Raman spectra is basically, according to Born-Oppenheimer approximation, we see that every spectroscopy has different energy level, but later we see that they are not differentiate, they are getting mixing with each other, like rotational plus vibrational. So this when a molecule when a molecule is excited with the light frequency to its higher excited state, then it also changing its quantum, changing in rotational quantum number J, along with when the molecule is excited, its size also getting changed, because when it excited, then its volume change, dipole moment generate. So the molecule also show rotation and also show Raman. So we can get this energy by this formula, that is rotational Raman is nu zero plus omega E 1 minus 2xc plus b 4j plus 6. In this case, delta j is plus minus 2 and the value of j is 0, 1, 2, 3. Sir, from this from formula, we can get the value of B and we can determine the rotational bond length of the molecule that are both Raman active and also rotational Raman active. As for example, H2.
Yes, what the basic difference Raman active and inactive molecule?
Sir, Raman active, active and inactive. Okay. Yes, and sir, Raman active and inactive molecule is Raman. The most criteria is the molecule must be changed in polarizability. So almost all molecule when they changes electronic or vibration, so vibration rotational, they are all changes. So therefore all molecule are Raman active, but one criteria is this, that the molecule which show mutual exclusion principle, in that case when they have one center of symmetry present in the molecule, in that case when one molecule, as for example CO2, if it is IR active, then it become Raman inactive, or if that molecule become Raman active and they are not getting IR, they are becoming IR inactive. Basically, the polarizability change.
Yes. Yes, how many factor affecting in rotational Raman spectra in nuclear spin? Stokes line, anti-Stokes lines, first Stokes lines, first anti-Stokes lines. What will be the effect?
Yes. Yes, sir. If it is delta J plus 2. Yes. Is that the effect is that it is change of rotational quantum number is it depend on the change in rotational quantum number. If delta J is equal to plus 2, if delta J is equal to plus 2, then it show O O line as like R line, and if it give delta J is equal to changing is minus 2, then it show S line, and if delta J is equal to 0, then it show Q line. So when we get a spectrum from that energy level by applying the rotational quantum number and exciting, then we get a spectra like this, that is Q line, and they are plus O line, and in that side we get S line. But comparing with the P and R branch, we see that their intensity getting become smaller. Their intensity getting become smaller with comparing with the P and R branch. And when the molecule are getting become heavier, then we cannot resolve them, and from the S and O we cannot resolve them, and from the S and O line we can getting the value of B, rotational constant.
Yes, good. Rotational constant is J is equal to 0 if value is J is equal to 0, 1, 2, 3. Rotational constant.
Yes, sir, rotational constant delta J equal to 0, 1, 2, 3.
Yes, what is the Stokes line, anti-Stokes lines or relay lines? What the value of rotational
Yes,
constant? Rhodes and Raman spectra.
If we putting the value of Stokes and anti-Stokes line, that is delta J is equal to 0, then this is become E is equal to nu 0 plus omega E 1 minus 2 xc. We always take it because it is the fundamental vibration. Then if we putting the value of J0, then it getting become plus 6b. Plus 6b, if we take delta J is equal to 0, and if it is become nu 0 plus omega E 1 minus 2 x E minus 6b, delta J is equal to 0. So plus 6b is anti-Stokes line and minus 6b is Stokes line. Similarly, if we take the value of 1, then it become formula that is minus 1 for minus 10b for minus 10b for it becomes Stokes line, and new plus 10b it become anti-Stokes line. So the distance between two line, so if we get the spectrum from the value, then we see that it is a fundamental vibration. So these are the anti-Stokes line, and these are the Stokes line. So first distance is 6b, and the all simultaneous distance become 4b in both two sides. 4b. Anti-Stokes.
What's the basic difference between even and odd lines? Even lines is miss. What
Yes, sir. Yes, sir. Even an odd line means that is if the rotational quantum number is J is equal to 0, 2, 2, 4, 6. These are the even line, and like J is equal to, in this case, 0, it is even line, and in this case J is equal to 1, it is odd line, and it is J is equal to 2, it is even line.
J is equal to?
J is equal to when the even number 0, 2, 4, then they are the even line, and if J equal to 1, 3, 5, then they are the odd line.
Yes.
If we put this rotational quantum number in the energy expression, then we get the that even and odd line.
Yes, good. Next one is vibration Raman spectra. What is vibration Raman spectra?
Sir, vibrational Raman spectra is when the molecule changing with changing polarizability, they are changes with their vibrational quantum number also, and when they excited to V is equal to 0 to 1 to 3, V equal to 0, 1 to 2, V equal to 2 to 3, then we get vibrational Raman spectra, and the energy level expression from the Schrödinger equation that we can derive, that is E is equal to vibrational vibrational
Yes, vibration
Raman, okay. Then we get energy expression omega fundamental at first fundamental plus nu 0 plus omega E 1 minus 2xe, 1 minus 2xe, and plus B 4J plus 6. Sir, in the case of vibrational Raman spectra, we only take the energy level expression of V is equal to 0 to V is equal to 1. In this case, also we see the fast Stokes line along with fast Stokes line, second Stokes line, and fast and hot band, but due to but hot band, but as the Raman spectroscopy, the intensity that we used or frequency of light that we use, this is very less frequency. So the fast Stokes line, anti-Stokes line, these bands are getting become neglected. So we only take the fundamental vibration in the vibrational Raman spectra, and the value of V is changing, vibrational quantum number changing 0, 1, 2, 3, and rotational quantum number changing 0, 1, 2, 3.
Yes, good. Nextly, vibration Raman spectra, any relation between the harmonic and harmonic oscillator? What will be the formula?
Yes, sir. In the case of harmonic oscillator, the formula of energy level expression is formula is nu V plus 1 by 2 into omega E minus V plus 1 by 2 square omega E xc. It is for harmonic oscillator formula. And in the case of vibrational Raman spectra, the formula is E is equal to exciting frequency plus only the 1 plus 1 by 2 omega E minus 1 plus 1 by 2 square omega E xc minus 1 by 2 omega E minus 1 by 4 omega E xc, and it is become E is equal to nu 0 plus omega E 1 minus 2 xc. So we only take the fundamental frequency, fundamental energy level formula with the exciting frequency of Raman, and it is the simple harmonic oscillator, vibration and harmonic and anharmonic. Difference.
Yes, good. Some point is right. The vibration Raman shift. What is a vibration Raman shift?
Yes, sir. Vibrational Raman shift is delta E is equal to exciting frequency plus minus omega E 1 minus 2xc, and is equal to nu 0 plus minus 2 omega E 1 minus 3xc, and is equal to nu 0 plus minus omega E 1 minus 4xe. Sir, these are the formula of vibrational Raman shift. That is nu 0 plus minus omega E 1 minus 2xe, nu 0 plus minus 2 omega E. It is generated from transition of molecule from V is equal to 0 to 1. It is the transition of molecule Stokes first Stokes line V is equal to 1 to 2, and it is from the V. It is the V equal to 0 to 2, and it is from it is the hot band V is equal to 1 to 2. With their exciting frequency, in case of Raman, we get the vibrational shift.
Yes. What the relation between vibrational strokes, anti-strokes, and relay lines in vibrational spectrum?
Yes, sir. Stokes line is when they are in positive term, means when they are in the higher energy but lower wavelength. That is the Stokes line. Like if it is new zero only, and when the line getting generated from negative wavelength, that is new zero minus omega e 1 minus 2xc, then we get um, like fast Stokes line. And in this case we get fast when the term become new zero plus omega e 1 minus 2xc, and new zero plus 2 omega e 1 minus 3xc, and new zero plus omega e 1 minus 4xc. So in that case we get anti-Stokes line. And when the term become minus, that means wavelength become their wavelength become getting smaller. Then we get Stokes line. And Stokes line have Stokes line have high intensity than their than the anti-Stokes line, because in the ground state always the molecules are present, population is larger.
Yes, good. Next is any relation between PQR branches in Raman spectrum?
Yes, sir.
Yes, what the relation?
Sir, basically PQR branch we see in the case of rotational and vibrational spectra. So in that case, the delta J, that is rotational quantum number, changes with 1 unit. Plus 1 is R branch, minus 1 is P branch, and 0 is equal to Q branch. But in that case, similar, when we get the formula, that is delta E is equal to nu 0 plus omega, that is the vibrational frequency, and plus b 4j plus 6 plus minus. So when the value of delta J is changing, when the value of J is equal to 0, 1, 2, 3, basically in this case delta J is changing with plus minus 2, not plus minus 1 in the case of Raman spectra or Raman spectra. So in this case we not see P and R branch. In this case we see O and H branch. O and H branch. So this is S branch and this is O branch. Comparing with the P and R branch, we see their P and R branch have getting higher intensity than the O and S branch. This is R and this is P, and S and O branch have less intensity because in this case the population intensity of light is smaller in the case of Raman spectroscopy.
Yes, good. What the selection rule of O and S branch? Vibration, rotation, Raman spectrum.
Yes. Yes, sir. In the case of rotational spectroscopy, the selection rule is for O is plus J is equal to plus 2, and S is J is changing is equal to minus 2.
वो ब्रांच del J is equal to plus 1 है, S is equal to plus 2.
Yes, sir.
Yes, next in case of vibrational rotational Raman spectra, what the selection rule of vibrational rotational Raman spectra?
Vibrational rotational Raman spectra. Sir, vibrational rotational Raman spectra is delta V is changing plus minus 1 plus minus 2, plus minus 3, and delta J is changing. Delta J is changing with plus minus 2. And the quantum number is 0, 1, 2, 3, and vibrational quantum number is also 0, 1, 2, 3. Yes, the vibrational quantum number changes with plus 1, plus minus 1, plus minus 2, plus minus 3. Although the intensity of the plus minus 2, plus minus 3 band are is smaller than the plus minus 1, and the rotational quantum number changing plus minus 2.
Yes. Plus minus 1 and plus minus 2.
Yes, sir.
Next is, what is the rule of mutual exclusion principle in Raman spectra? What the main application and objective of mutual exclusion principle?
Yes, sir. In the rule of mutual exclusion is basically when any molecule has center of symmetry. Center of symmetry means the two atoms are present with center in the same distance in opposite direction. So when the center of symmetry present, then the molecule that are become IR active, then they are Raman inactive, and if they are Raman inactive and they are become IR active. So it is an experimental phenomena. From this rule of mutual exclusion application is, if there is any center of symmetry present like CO2, and if their spin is become 0, then the even line getting become vanishes in their molecular spectra. And if the in the case of oxygen is I equal to 0, and in the case of CO2, if their I is equal to 0, then the odd line getting become vanishes in their rotational vibrational Raman spectra. So we get alternative line. So we get alternative line in their band. That is 0, 1 is present, 2 is vanishes, and then 3 is present. 3 is present. So the distance getting become 8b in respect of 4b. Then the new distance getting become 8b.
Yes, good. Yes, what the relation between in case of SO2 and CO2 molecule in mutual exclusion principle? Raman active, IR active.
Yes.
Can you describe?
Yes, sir. In case of SO2, SO2 is in case of SO2. So it is a bent. Basically, if we see the structure, it is a bent molecule. Yes, it is bent. And in the case of CO2, it is a linear molecule. So in this case, center of symmetry is not present, but in this case, center of symmetry is present. Center of symmetry present. And in this case, center of symmetry not present. Center of symmetry not present, center of symmetry present. And in this case, in this case, the spin is become 0. I is equal to 0, and in this case, I not equal to 0. So if I equal to 0, then the case of CO2, the odd line getting become vanishes in their spectra. Odd line not present, and in this case, all the line will be present. All the line will be present. So from the spectra, if we see their spectra, then we see it is the incident line, V is equal to 0, exciting frequency, then V is equal to 0, then V is equal to 1, then V is equal to 2 line. So this V is equal to 1 line getting not present. The distance is at first 6b and 4b. It changes in the distance to 6. V is equal to 0 to odd line not present. Distance getting become 10b, but